Hi, in this video we're going to talk about basics of gases as they apply to chemistry. Now this is pretty much a summary video. As with pretty much everything during the pandemic, I'm running out of time, and so at some point in a few months, hopefully, I will be posting a more thorough study of gases, but in the meantime this should cover a lot of what you need to know. So let's start out by talking about what people figured out by observing gases. First of all, gases seem to be mostly empty space. So you have some molecules in there, but there's a lot of room in between those molecules. Second of all, you've got molecules moving at very high speed. But exactly how fast they're moving is related to the temperature. So the higher the temperature, the faster the molecules are moving, and the lower the temperature, the slower the molecules are moving. That's actually related to the definition of temperature that we talked about in the last chapter. As those molecules move around, if they're in a container of any sort, they're going to crash into the walls of the container. So those were the things that you can figure out by observing gases. And this has led to what people call the Kinetic Molecular Theory of gases, which basically tells us the following things. First of all gases consist of tiny particles that are randomly moving around. Those tiny particles may be individual atoms if you have an elemental gas, or they could be molecules. But most of the volume of the gas is empty space. As these particles move around, in part because a lot of what's between them is empty space, but also just because of the nature of gases, there are usually no forces that are either attracting particles to each other or repelling them from each other. When you have collisions, we assume that they're elastic. What this means is if a particle is moving with a set amount of kinetic energy, when it hits a wall, it bounces off and it has exactly the same amount of kinetic energy. And again, let's just remember that the kinetic energy is proportional to the temperature in Kelvin. It's really important that we understand that we have to be using an absolute temperature scale when we talk about these things, because if you have a negative temperature, what does that mean for your energy? All right, so one of the things you really need to understand before you dive into any study of gases is the concept of pressure, which is really the amount of force that is being applied in a particular unit of area. And perhaps one easy way to understand it is what would happen if you put two masses, which are exactly the same masses, but spread that mass out over a large area versus concentrated it in a small area. So for example, let's say that you get a choice. Someone is going to step on your foot, and that person is going to weigh exactly 150 pounds. But you get a choice of what shoe that person is wearing. So here are the choices. You can either have this lady with the high heel, or you can have the lady wearing the sandal. Now, I don't know about you, but I think that having the person in the sandal step on my foot would be better, because having that heel go on my foot where I have 150 pounds mostly concentrated on that one teeny tiny spot. So let's talk about units of pressure. Obviously, as with everything, there is an SI unit, which is a Pascal. This is a derived unit, 1 Newton per meter squared, and that ends up working out to 1 kilogram per meter second squared. The Pascal ends up not being a really great unit to measure pressure with because it's a really tiny unit of pressure. This kind of goes back to what we were talking about in regards to the joule as well. Remember, joules are really tiny and we usually end up using kilojoules or even megajoules. So the same is true of pascals. Now, if you want to talk about old-fashioned non-metric /SI units, the unit of pressure you're probably most familiar with is atmospheres. 1 atmosphere is 101,325 pascals. Now, the Pascal is too small to be really useful in terms of measuring, but an atmosphere is too big. It's great if you're talking about, let's say, planetary processes, like here on Earth, or, one of the other planets, like Venus, has a much thicker atmosphere than Earth, and it has stronger pressure. I believe it's something like 90 atmospheres. But when you're talking about generating small amounts of gas in lab, an atmosphere is just way too big of a pressure unit. Now, like I said, the atmosphere is old traditional unit of pressure, and there is a metric unit that's a lot more useful than the Pascal, and that is 1 bar. 1 bar is 100,000 pascals, and it turns out that is just over 1 atmosphere, so 1 bar has sort of become the standard metric unit when you're talking about planetary processes. But again, it's close to 1 atmosphere. This is too big for most lab work. The units of measurement you'll often see if you're measuring things in lab is a torr or a millimeter of mercury. These are equal to each other. And 1 atmosphere is 760 millimeters of mercury or 760 torr. So as we talk about pressure in this unit, most of the time we're going to be using atmospheres or torr. So as people studied gases very early in the history of science, they started discovering relationships. For example, Boyle discovered a relationship between pressure and volume. So if he had a cylinder with gas inside it, it might have a volume of 1 liter with 1 atmosphere of pressure pushing on the outside. But if the external pressure was increased to 2 atmospheres, then the volume would decrease to half a liter. In other words, pressure and volume are what we consider to be inversely correlated. When one goes up, the other goes down. And the way we express this mathematically is we say that pressure times volume equals some sort of constant. Now, if you're comparing what happens before and after, you can say the pressure of what happens at the beginning times the volume in the beginning is going to equal the pressure at the end times the volume at the end. So in this particular case, 1 atmosphere times 1 liter, which is what we started with. 1 times 1 is 1. 2 atmospheres times 0.5 liters, which is what we had at the end. That would be 1 as well. Gay-Lussac discovered a relationship between pressure and temperature. So here, this scientist was keeping things at a constant volume and noticed that when the temperature was increased, let's say from 200 Kelvin to 400 Kelvin, the pressure would increase. So it got hotter and the pressure was higher. So what does this tell us mathematically? Temperature and pressure are correlated. As one goes up, the other goes up. And so if you divide the pressure by the temperature, you'll always get a constant. Another way you can think of this is that the pressure at the start divided by the temperature at the start is going to equal the pressure at the end divided by the temperature at the end. Okay, here's another relationship that was discovered, something that we call Charles's law. This is a relationship between volume and temperature. This experiment was done with a constant pressure, and what was discovered is if the temperature cools down from 300 Kelvin to 150 Kelvin, let's say, the volume would also decrease. So again, volume and temperature are correlated. Volume divided by temperature is a constant, or we could write this as volume at the start divided by temperature at the start equals volume at the end divided by temperature at the end. Now, one more law that we're going to talk about is Avogadro's law, and yes, it is that Avogadro. So In this particular experiment, pressure and temperature were both kept constant. And what was done was that the number of moles of gas inside this container were changed. And that affected the volume. So if the number, for example, went from 2 moles to 1 mole, the volume decreased from 1 liter to half a liter. So again, volume and numbers of moles are correlated. Volume divided by numbers of moles are a constant. And again, we're just going to write this way. Now, I know that is an awful lot of laws to remember, and conveniently, you don't have to remember them all. Yes, there were a bunch of old dead white guys who long ago discovered these various relationships, and we're grateful for their work. However, if you think about what I just talked about, I talked about a relationship between pressure and volume, pressure and temperature, volume and temperature, and volume and numbers of moles, and you think, all these things are related to each other. Wow. So we have this thing that we call the ideal gas law, which combines all of those gas laws into one gas law. A lot of times when people look at this name, the ideal gas law, they say, what's so ideal about this gas law? Is it that it combines everything? Well, that's not what it is. This is a law that affects ideal gases. So we're not talking about the law being ideal, we're talking about the gases being ideal. And so the characteristics of an ideal gas are things that we talked about earlier. They're gases that have molecules that don't interact with each other. They're gases whose molecules aren't so huge that most of the volume in a container of gas is empty space, and the volume that's occupied by the actual gas molecules is really teeny tiny compared to the total volume of the container. So if those exist, then this ideal gas law applies. If it doesn't exist, there are slightly more complicated gas laws, and we're not really going to talk about that in this class. So here's the ideal gas law. PV equals nRT. P, of course, is pressure. V is volume. N is the number of moles. T is the temperature, which has to be in Kelvin always. And then we have this R, which is a gas constant. Now, if you look up the gas constant, you will find an amazing number of different values for that gas constant. And it's important to find one that has the right units. And so in general, the two most commonly used values for the gas constant are this one that I have highlighted, 0.0821, and that's the one we're always going to be using in this chapter. And the other one is 8.3145 joules per mole Kelvin, and that is one that we use when we're calculating energies. So you will see a lot of the second value of R as we get into Chem 2, but for this chapter, we're always going to be using the 0.0821 liters, atmospheres per mole Kelvin. And you'll notice those units relate volume, pressure, numbers of moles, and temperature. So let's go ahead and do a problem. In general, when you do an ideal gas law problem, you're going to think about the variables in the ideal gas law. As you read through the problem, identify which numbers go to which variables, because there are a lot of variables. Of course, R, we're always going to know, that's always going to be this value right here. But as you read through this, a sealed 10.0 liter balloon, well, 10.0 liters are a volume unit, so that's going to go right there. Full of helium, has an internal pressure of 1.57 atmospheres. Again, that's a pressure. At 30 degrees Celsius. That sounds like a temperature to me. How many moles of helium are in the balloon? So now we know 3 of our 4 variables plus the constant we need to know. The problem is that our temperature needs to be in Kelvin, and here it's given in Celsius. So let's convert that, and we see that it will be 303.15 Kelvin. Let's take those numbers now and let's just plug them in. The only one we don't know is N, so we need to isolate that, and we're going to do that by dividing through by our R and T values. You'll know that you've set it up correctly if the units all work out. So we have atmospheres canceling, liters, kelvins. We're left with moles in the denominator of a fraction that's in the denominator of a fraction, so we should end up with moles. So 0.631 moles. Here's another question. Of course, we already know our gas constant. So a sealed chamber with a fixed volume of 20 liters, that's our volume, contains 1.16 moles of gas. If the chamber is heated to 400 Kelvin temperature, what is the pressure of the gas? So we know everything except the pressure, and conveniently we see that the problem asks us to find out the pressure. So let's go ahead and plug those numbers into our formula. Conveniently, our temperature is in Kelvin this time. And now we can solve for pressure by dividing through by our volume of 20 liters. And again, you'll notice that moles cancel, liters cancel, kelvins cancel. We're going to have a final pressure in atmospheres. And so that equals 1.90 atmospheres. Now, in the two problems I've done, you'll notice that I used pressures in atmospheres. Sometimes you will be given pressures in torr. Now, it's possible you might be able to find a value of the gas constant that has units of liters torr per mole Kelvin, in which case you can go ahead and use that. But if you don't have that, then you may need to convert atmosphere to torr. Remember, 760 torr in an atmosphere. So why do we care about this in chemistry? Because these relationships between pressure, volume, temperature, and numbers of moles help us with stoichiometry problems. Because there's a direct relationship between numbers of moles and volume, we can measure gases by volume when we're doing stoichiometry problems. That assumes that the pressure and the temperature stay the same, but you can also imagine what would happen if there was a chemical reaction going on and that changed the numbers of moles in the system. And also, because it's, let's say, an exothermic reaction, what happens if the temperature goes up? Ooh, now we're getting complicated. Anyway, these things all tie together, and it ends up being really important in figuring out what happens to a system as it goes through a chemical reaction. I hope this was helpful, and I look forward to seeing you again soon.